our favourite space telescope seems to be really pulling everything out of the bag, doesn't it, Terry?
Yeah, absolutely. I mean, this just sort of is getting more and more unbelievable. The launch and deployment and commissioning and so on of the James Webb Space Telescope is by far the most complex operation that has ever been attempted in space, particularly as it's all done remotely. Uh, Started off basically once it sort of got out of Earth's orbit, things started to happen. But now everything is happening at a distance of almost 1,000,000 miles. And as I say, it's incredibly complex. Every single stage that has happened up to this point has been mission critical. And yet everything has gone, as the Americans would say, nominal, which means basically it's worked perfectly. And it's almost too good to be true. And I hope that's not putting a hex on it. So we have followed the progression of the deployment and the alignment and so on every program since it launched. The latest one is that all 18 of the mirror segments, which you're probably familiar with, the hexagonal gold-coated mirror segments, are now functioning as one giant mirror. So the 18 separate images that we showed you last time when they were testing have all now been combined into one. And the result of that is that image is now so bright that they've had to switch to a slightly fainter star. Otherwise, the image would be so bright that it would be impossible to get a fine detail in it. So the first star was magnitude 7 roughly, and the latest one that they're using now is magnitude 8.8, just about what the limit of what you can see in a good pair of binoculars. So this is actually the third of 7 total phases that they go through before the mirror is absolutely totally 100% accurately aligned. It's called segment alignment and image stacking. And by the way, they've also now perfectly aligned the secondary mirror, which of course is an equally critical thing. Now, the point about this is the accuracy that they need to achieve is unbelievable. It's about a 10 millionth of a meter. Every single mirror has to be exactly aligned to that degree of accuracy and to function together as one huge mirror of that size. The next phase, which they're now starting, that's underway, is what's called coarse phasing. And one of the instruments, the NIRCam, NIRCAM, near infrared camera, it will be taking spectra. In other words, splitting up the light from the star from 20 pairs of mirrors, and that in a sequence that will allow very accurate vertical positioning of the mirrors. As I say, they not only have to be aligned with each other to that degree of accuracy, they have to be exactly the same distance away from the secondary mirror to an accuracy of a 10 millionth of a meter. And by splitting the light up into the spectra, that enables you to make very fine adjustment. So that is ongoing at the moment. I hope this isn't putting a hex on it, but basically everything so far has worked perfectly. And, barring unforeseen incidents or some snag that we can't imagine at the moment, it is going exceedingly well. And it looks as if this telescope is going to soon, about July, I think, before everything is finally commissioned and tested, including the instruments on board, not just the optics, we're going to see some absolutely amazing results from this telescope. I'm sure you'd agree, Nick.
Absolutely, and you only have to look at, in standard astronomical terms, us amateur astronomers up to professional astronomers, we have to do this with telescopes. It's collimation, it's basically mirror alignment, etc. But this is taking things to a whole other level. Things like the point spread function, for example, the kind of the optical competency, as it were, of the system, as you said, has got to be off the scale. I mean, they're looking at image resolution that's never been achieved before. It's a really good question, actually, as well, from somebody I know quite well via Twitter. Chris, who basically has brought up this question about deployment. Is it as complex as the Hubble servicing, or, for example, building the ISS? It's a very good question. You think about it, the Hubble deployment and the Hubble servicing missions, that was all, a lot of it was handled out of SSCO and the NASA Goddard spaceflight team. And I know people like Ed Razak who worked there, who worked on the Hubble servicing team tools and trained up a lot of the astronauts in building those tools. that was incredibly complex, but it was only at 450-kilometer orbit away from the Earth. So were things to go wrong, they would have a second shot at it, or they could basically, almost recover from it. And having humans in the loop does make things, as we saw with the Apollo program, a lot easier. You only have to look at the Mars rovers, for example, and how complex it is even to get very small samples, drill cores, etc., into sample tubes and have them there for future retrieval, whereas on the Apollo missions, having humans on the moon, very easy to pick up the rock. So having humans in the loop in any system tends to make it obviously more challenging in some respects, but a lot easier in others, in that people can make very quick decisions. If you've got the James Webb, which is a completely autonomous system, it had to deploy hundreds of separate components to a level of precision that nobody had ever seen before, and to be tested. And don't forget, it was never integration tested on the Earth. It couldn't be because it's too large. You could never do a full integration test of both the main mirror, the instrumentation section, and the sun shield in one go, because it was just too big for any TVAC or vacuum chamber anywhere on the planet. So in terms of against the Hubble, I'd say more complex. The interesting thing with the Hubble, the cost of some of the servicing missions, they could have built a new Hubble and launched it. And that's that's the thing that they can't really do with the James Webb. There was talk this week talking about things like Starship and being able to send out a Starship mission, but then you've got to build an orbiting platform. You've got to be able to get out there, you've got to be able to service it in situ. It would probably cost almost as much in the long term as the initial cost anyway. I mean, the overrun costs on the James Webb are quite spectacular, but really, really, achievement has been kind of they've got there in the end, but despite the overrun costs. Against the ISS, again, it's a very interesting question, because the ISS, you've got something the size of a football pitch, and you've got, again, the largest structure ever put into orbit, and there's all sorts of ramifications now with what's happening in the Ukraine with the ISS, etc., and we'll go on to that in a little bit. But in terms of building the ISS, again, you had humans in the loop, and you had the shuttle as a very well known and capable delivery system, along with the Soyuz delivery systems as well, for various stages and various instruments, etc. And you're at a relatively low orbit and relatively short distance from the Earth, so if things were to go wrong, or things were to be misplaced, or a spanner was to be lost, or a bolt was stripped, with the Hubble, for example, there's talk, the Mike Massimino book, if you've ever read it, where he literally had to kick the door off because one of the screws had threaded to access some of the components that they were aiming to repair on the Hubble during one of the last servicing missions. Massimino talks about in detail in his book, and how terrified he was that he was going to get it all wrong, and they had to build the capture plate system, where the screws, obviously, when they remove the screws, obviously you're in a microgravity environment, you don't want screws drifting around everywhere and adding to the already enormous debris problem that we've got. So I'd say, from a technical standpoint, as a single point of failure mission, as it were, with a completely autonomous system, this is probably the most complex that's ever been achieved. You look at some of the deep space missions, New Horizons, the Huygens landing on Titan, etc. They're incredibly complex, but I think this one, probably along with Rosetta, and the orbital dynamics on Rosetta just still blow my mind. But again, you've got humans in the loop there. It's not a completely autonomous system. I think with James Webb, it's a case of it was fire and hope, and they had to work. So yeah, it's a really, really good question, Chris, and I'd say probably up there in terms of the most complex thing ever achieved in space.
I think the difference with the ISS is that there are a whole lot of separate components, and what if one of them failed or didn't attach properly, that wouldn't affect the operation of all the rest. In terms of the JWST, if they don't get the optics right, the whole thing is a failure. So it's mission critical to get the optics perfectly aligned.
Well, that's the thing. And also, you're looking at a radiation environment that is well beyond what the Hubble is experiencing as well. We're looking at deep space radiation environments. So the electronic components, all of this, don't forget, as it's an automated system, is relying on computational systems to do the deployment. So all of that's got to be able to sustain, high levels of what's called TID, kind of disruption events, C events as well, which are all kind of radiation specific events that can really knacker up onboard computers. On top of that, you've got whatever micrometeorites, you've got a whole ton of things that could potentially go wrong. And when you're looking at the level of precision here, and the only time I've ever seen a level of precision equivalent to the James Webb, I think is probably one of the ESA missions where they were looking at gravity wave detection, the LISA Pathfinder and LISA missions, where essentially they had two beryllium spheres, two beryllium cubes in the LISA mission anyway, planned they were going to be about 1 million kilometers apart, and they were going to be able to detect a gravity wave based upon the deflection of a laser between these, and the incident angle of that deflection was the equivalent of apparently your thumbnail at around about the orbit of Neptune, the width of your thumbnail. So it is astonishing what they're doing here.
Yeah.
We've got to keep on top of this one. As Chris has said in the chat as well, it's not just, we talk about the 7 minutes of terror and that amazing video that NASA put out with the Curiosity landing and Adam Stelter, etc. This is 7 months of terror. This has got to go right at every single stage, and so far they've nailed it. As you said, they're on point. It's a nominal mission. So I personally can't wait to see what a proper first light's going to be now that we've got a star, and they've not even focused that star yet. You look at that image, and most ground-based telescopes would think, "Oh, that's a brilliant image." That's not even close to what they're aiming to achieve. So, they're going to be able to resolve details on the surface of Betelgeuse of this thing quite happily. Sunspot details, etc. So bear that in mind. It's off the scale.